Tonight, you are leaving the solar system. Not to colonize another world, not to wake beneath a second sun, not even to stop when you arrive. You are simply trying to make one human-built machine reach Alpha Centauri while it can still remember how to speak. You are a gram-scale probe attached to a sail. Your camera, processor, power source, navigation system, and transmitter have been compressed into a body that weighs less than many coins. Behind you, on or near Earth, a vast array of lasers waits to become the engine you cannot carry. Ahead of you is a target more than 4 light-years away. Between the two is almost nothing, which would be reassuring if almost nothing did not become dangerous when you cross it at a meaningful fraction of light speed. Before we start, take a quick moment to like the video and subscribe, but only if you genuinely enjoy what we do here. Now, dim the lights, pull the blanket up, and settle in. You are currently inside a room that does not need a laser array to move, a microscopic computer to navigate, or 20 years of silence before anyone knows whether it survived. Let's take a break to answer a few questions. Can your sail survive the beam that must accelerate it? Can your electronics remain functional after an acceleration no human body could tolerate? Can a grain of dust erase the mission in less than a second? Can you aim at a star system that keeps moving for the entire voyage? Can you correct your path after the engine remains behind on Earth? Can your sleeping hardware wake after 2 decades in interstellar space? Can you slow down when there is no laser waiting at the destination? If you cannot slow down, does a flyby lasting hours count as arrival? And if your camera succeeds, can a transmitter smaller than your hand send the image across more than 4 light-years? The laser array fires. Light strikes the sail and changes direction. That change transfers momentum. You begin accelerating without burning propellant, and within minutes the familiar architecture of the solar system collapses behind a rising number on a tracking screen. The moon is no longer a distant destination. The planets are no longer separate expeditions. The beam holds, the sail remains centered, and your tiny body endures a force that would reduce a human passenger to biology with nowhere useful to go. Then, the laser switches off. Congratulations. You survived acceleration. Earth is already shrinking behind you. Alpha Centauri is still more than 20 years ahead. Your engine cannot follow, your hardware cannot be repaired, and the velocity that made the voyage possible has become the first thing threatening the mission. It is speed. Speed is the reason you can imagine arriving while some of the people who launched you are still alive. It is also the reason the empty space ahead can damage you, the reason your target will pass in a blur, the reason a small navigation error becomes enormous, and the reason the word arrival may mean nothing more than crossing a coordinate before vanishing into the dark again. For a machine moving between planets, speed usually feels like progress. For you, speed becomes the environment. The proposed target is roughly 20% of the speed of light, close to 60,000 kilometers every second. That number does not describe a spacecraft operating today. It belongs to ambitious directed energy concepts such as Breakthrough Starshot, which investigate whether an immense laser array could push a gram-scale sail to a relativistic cruise speed. The physics of light carrying momentum is established. The complete machine required to turn that physics into an Alpha Centauri mission has not been built. Your body exists because the design attacks the mass problem without pretending the energy problem disappeared. A conventional spacecraft carries fuel and engines. You leave the main power source behind. Photons cross the gap between the laser array and your sail, reflect, and transfer momentum. The array remains near Earth, where power, cooling, maintenance, and large optics are possible. Only the sail and tiny scientific payload must accelerate. That trade saves mass and creates dependence. During the minutes of acceleration, you cannot leave the beam, cannot allow the sail to absorb too much light, and cannot correct a large mistake with an engine of your own. The largest part of your propulsion system is a distant machine trying to hold light on a target only meters wide, while that target becomes faster and farther away every second. If the array is on Earth, the atmosphere moves above it. Warm and cool cells bend the beam. Adaptive optics must measure those distortions and correct them in real time. Thousands or perhaps many more individual emitters must operate with their phases controlled so their light combines in the intended direction. The beam must track your accelerating sail, account for the changing geometry, and avoid illuminating aircraft, satellites, or other objects that have no interest in joining an interstellar mission. The beam is not a bright line visible from the side as it would appear in an illustration. Most of its light travels along the path toward you. What matters is not how dramatic it looks from a distant camera. What matters is whether the wavefront reaches your sail with the shape, power, and precision the control system expects. Your sail has a second job beyond reflecting light. It must remain stable while light pressure pushes it. A perfectly flat sheet can tilt, drift, flex, or tumble if the pressure is uneven or if the center of force does not align with the center of mass. Proposed designs explore curved sails, patterned materials, and beam profiles that could create restoring behavior. The objective is to make small errors move you back toward the beam center instead of pushing you farther away. This is not decorative elegance. At the velocity you are gaining, a tiny angular departure writes a different address into the next 20 years. There is no rescue tug waiting beyond Mars. If you leave the useful beam early, you may remain an impressive fast object and still fail to approach Alpha Centauri. A sail can reflect nearly all incoming light and still absorb a small fraction. When the beam carries extraordinary power, a tiny fraction is no longer tiny in thermal terms. Your material must reflect the chosen wavelength extremely well, radiate absorbed heat, preserve its shape, and remain only a few grams. A thicker heat-tolerant structure may survive better and accelerate worse. A lighter sail may accelerate beautifully until it deforms. The first opening question, therefore, has a conditional answer. Can your sail survive the beam? Known physics does not forbid it, and laboratory work can investigate candidate materials, stability, reflectivity, and thermal behavior. But survival at the full required scale is one of the mission's major unsolved engineering gates. You did not survive acceleration because the problem is already solved. You survived because our simulation grants the future architecture the performance its own mission requires. During those minutes, your average acceleration could reach around 10,000 times the gravitational acceleration felt at Earth's surface. You do not experience weight as a person does. You have no bones, vessels, lungs, or inner ear. Yet your electronics, coatings, connections, and sail still experience force. Components must remain attached and aligned. The wafer must not crack. The sail must not wrinkle into a shape that changes the pressure pattern. This pays the second question. Can your electronics survive an acceleration no human body could tolerate? Compact solid-state hardware can be designed for accelerations far beyond human limits, but the complete payload must be tested under representative loading. The absence of a human passenger is the enabling feature. Shrinking the craft does not merely reduce energy, it allows a launch profile that biology cannot enter. You have now crossed the first threshold, but the launch array cannot continue pushing forever. The beam spreads with distance. Keeping it focused on a meter-scale sail becomes progressively harder. Eventually, the useful acceleration phase ends, and the mission transitions from a few violent minutes to decades of nearly unpowered cruise. You survived the beam. The laser that moved you remains behind, already separated by a distance growing at tens of thousands of kilometers each second. Your sail can no longer treat it as an engine with an unlimited throttle. Any later course correction must come from whatever control authority your tiny body carries, or from pressure exerted by natural light. The velocity is mostly fixed. Now compare yourself with the machines that first taught humanity to cross deep space. Voyager 1 moves away from the Sun at roughly 17 kilometers per second. At that speed, a craft aimed toward Proxima would need on the order of 75,000 years. Voyager itself is not heading there and cannot be redirected toward it. Its speed serves only as a ruler for an outbound velocity humanity has actually sustained. You would cover in hours what Voyager covers in years. That comparison sounds triumphant until you remember how the gain was purchased. A payload measured in grams, an immense beamer, acceleration of thousands of gravities, no crew, almost no fuel, and no easy way to stop. Parker Solar Probe offers a larger record number, reaching about 700,000 kilometers per hour near the Sunday. But Parker gains much of that speed while falling deep into the Sun's gravity on a carefully shaped orbit. Its record velocity near closest approach is not an outward cruise speed that can be pointed at another star. You are not borrowing a number from Parker. You are attempting to leave the Sun with an extraordinary excess velocity that remains after the gravitational climb. The distinction changes how you see the solar system. Planets no longer serve mainly as gravity assist stations because your acceleration happens through beamed light. The Sun's gravity still pulls backward as you depart, but at the proposed cruise velocity, it cannot reclaim you. The familiar planetary architecture begins shrinking into a compact region behind. Mars's orbit passes. The giant planets become distant geometry. The region explored by generations of robotic missions ceases to feel like the journey and becomes the launch neighborhood. Your clock does not mark long planetary transfers, it marks the gradual fading of the only star whose power infrastructure knows your design. The Sun surrounds itself with a heliosphere, a vast region shaped by the solar wind and its interaction with the local interstellar environment. Voyager took decades to cross the heliopause, one important boundary where the solar wind no longer dominates the surrounding plasma. At your assumed speed, the broad scale of that crossing arrives quickly, compared with the decades ahead. The heliopause is not a glass wall. Plasma density, magnetic fields, and particle populations change. The boundary moves and responds to solar and interstellar conditions. You pass from a region organized strongly by the Sun's outflow into the local interstellar medium. The light behind you weakens. The material ahead remains sparse. That is when almost nothing begins hitting you. Interstellar space is not a perfect vacuum. It contains gas, charged particles, magnetic fields, cosmic rays, and dust. The density is extremely low by the standards of air. Your speed changes the encounter rate and energy. You sweep through an enormous column of space, and every atom that crosses your narrow frontal area arrives at a relative velocity determined mainly by you. Imagine one hydrogen atom. It is not a bullet in ordinary life. At a substantial fraction of light speed, its collision deposits energy into a small region of material. Heavier atoms can leave damage tracks. Dust grains, though microscopic, carry far more mass than individual atoms and can create craters, melting, erosion, or vaporization at the impact point. The phrase grain of dust is almost misleading because it invites you to picture something visible on a table. Many relevant particles are far smaller. You may never detect them before impact. Your camera is not a windshield observer searching for specks. It lacks the aperture, power, and response time required to see every dangerous particle far enough ahead for avoidance. The solution is not heroic steering, it is architecture. You orient the smallest practical frontal area toward the direction of motion. Sensitive components sit behind protective material. A coating or sacrificial shield absorbs cumulative damage. Functions are distributed, so one microscopic crater does not automatically erase every system. Multiple probes launch along related trajectories because redundancy across a swarm may be lighter than making one craft invulnerable. Each choice changes something else. Protective material increases mass. Increased mass lowers acceleration for the same beam or demands more light. Turning the sail edge-on may reduce impact area but complicate attitude control. Discarding the sail can reduce vulnerability, but the sail might have helped with navigation or communication later. Keeping it gives you a large structure that must survive 2 decades. Scientific studies of relativistic spacecraft interactions with gas and dust estimate surface erosion and deeper material damage under particular assumptions about velocity, material, and the interstellar column. The estimates are not a map of each object you will hit. They are warnings expressed as distributions and expected cumulative effects. The precise corridor to Alpha Centauri has never been surveyed by a fast craft. Can one grain erase you in less than a second? A sufficiently massive particle striking a critical region could disable or destroy a gram-scale probe. We do not know the exact probability for a final architecture and route, and inventing one would create false confidence. We know that impact risk increases with velocity, that small frontal area helps, that shielding and redundancy matter, and that the uncertainty is serious enough to shape the mission. You cannot make the road clean. You can make the attempt plural. Instead of one perfect sail, imagine a launch campaign sending many. Some may fail to ride the beam. Some may drift. Some may suffer impact damage. Some may lose their transmitters. If enough survive, the mission can still return science. The group can sample different parts of the medium and perhaps cooperate in communication. This changes the emotional unit of success. You are no longer a flagship promised an intact arrival. You are one member of a population. The mission can accept individual silence without accepting total silence. That sounds cold only because human spaceflight stories usually give every vehicle a name. Nature often uses another strategy. Send many seeds and let probability meet distance. You survive the first impacts. There is no sound, your body is too small to contain a cabin, and space provides no air to carry an external bang. Damage appears as altered material, a corrupted sensor, a changed thermal surface. Your onboard logic must decide whether the difference is temporary noise or permanent loss. Earth cannot inspect the crater. By the time a detailed report reaches mission control, the report itself is old. By the time a response returns, you have traveled farther than any repair team could follow. The third opening question has now paid its first answer. Dust can end the mission, but not because interstellar space is secretly crowded. It can end the mission because speed turns rare microscopic encounters into high-energy events, and because your tiny body has almost no room to place damage somewhere unimportant. Congratulations. You survived the first enemy created by your own velocity. Now you must remain alive while doing almost nothing for 20 years. That may be harder than it sounds. Activity consumes power. So does survival. Your processor must keep time, monitor components, preserve memory, control attitude, decide when to wake, and know when the destination is close enough to demand full attention. Near Earth, strong sunlight can supply energy to a collector. Far from the sun, and not yet close to another star, the light available to a tiny surface becomes weak. You need a power strategy designed for the long middle. A small radioisotope source is one option considered for gram-scale interstellar concepts. Radioactive decay releases energy without sunlight, but the source, conversion system, shielding where required, and storage all consume mass. The continuous power may be extremely small. A capacitor or battery can collect energy slowly and release it during brief periods of computation, navigation, or transmission. You therefore do not spend 20 years behaving like a busy planetary orbiter. You sleep. Sleep is an analogy. Your hardware enters low-power states. Most instruments remain off. Timers and minimal monitoring continue. At planned intervals, systems wake, check temperature and orientation, compare sensor readings, update an estimate of position, and decide whether the mission remains inside acceptable limits. The dangerous part is that every wake-up depends on something that has also been aging. A clock can drift, radiation can flip bits, memory cells can degrade, microscopic impacts can change electrical behavior, materials expand and contract as thermal conditions vary. A fault that would be trivial in a laboratory becomes permanent if the software cannot isolate it. You cannot call Earth and wait while an engineer opens the correct manual. At first, communication delay is measured in minutes or hours, then days, then months. By the time you are 1 light year from home, a command takes a year to reach you. Near Alpha Centauri, a full question and answer exchange requires more than 8 years. The distance does not merely slow control, it abolishes control on the timescale of an emergency. Your autonomy must be more than a list of scheduled commands. Sensors may disagree. One camera pixel field may be damaged. A star tracker may fail to recognize a pattern. Stored navigation data may remain correct while the clock feeding it has drifted. Your processor must distinguish an actual change in the environment from a failing instrument, then choose an action whose consequences no person can inspect until years later. More computing would help and cost mass, power, and reliability. More sensors provide comparison and create more components that can fail. Identical backups can share identical weaknesses. Diverse backups weigh more and require different software. The same trade that shaped your shield now shapes your mind. This is why some advanced studies examine swarms rather than isolated probes. Many small craft can carry different instruments, compare timing, relay information, or combine signals. A group can lose members without losing every measurement. If several surviving probes transmit coherently, their combined optical signal may be easier for Earth to detect than a single weak source. But a swarm is not a cloud of friendly lights, effortlessly agreeing with one another. Each probe needs to know its time and approximate position. Signals among probes also take time to cross their separation. Members drift. Some clocks fail. Coordinated transmission requires rules written before launch and robust enough to operate after the group has changed. Your mission might instead use the swarm statistically without demanding constant cooperation. Each probe flies a related trajectory and attempts the same essential observations. Earth combines whatever returns. That sacrifices some collective capability and reduces coordination risk. Again, the architecture decides which kind of failure is easier to survive. You wake for another check. The sun is now one bright star behind you. It no longer fills a large disk in your sensors. Earth is hidden close to it from your perspective, tracing a tiny orbit that matters mainly for communication pointing. Ahead, Alpha Centauri still appears as unresolved light, but your navigation system does not aim at the light's current observed position. The system moves. Alpha Centauri is not one star. Alpha Centauri A and B form a bright binary pair, orbiting each other over roughly 80 years. Proxima Centauri, a small red dwarf and the nearest individual star to the Sun, is bound far from the pair on an orbit lasting more than 500,000 years. A mission to Proxima is not automatically a visit to A and B. The separation inside the system can span thousands of astronomical units. Your chosen target is Proxima Centauri, and, if encounter geometry permits, its planet Proxima b. The red dwarf lies about 4.25 light-years from Earth, slightly closer than Alpha Centauri A and B. That fraction of a light-year looks small on a star chart. Inside the system, it is enough to make Alpha Centauri an address containing several distant neighborhoods. You do not point at where Proxima appears today. The light entering a telescope on Earth left more than 4 years earlier. Astronomers model the star's motion through space. The sun's motion, your velocity, and the planet's orbit. The launch direction aims toward an intercept point, where target and probe are expected to meet decades after the beam switches off. Proxima b completes an orbit in about 11 Earth days. During your cruise, it circles its star hundreds of times. The planet does not need to be predicted from one ancient snapshot. Repeated observations constrain its orbital period and phase. Yet every measurement carries uncertainty, and the desired flyby corridor is tiny compared with 4 light-years. The fourth opening question now becomes personal. Can you aim at a system that keeps moving for the entire voyage? Yes, in principle, because stellar and planetary motion can be measured and modeled. The challenge is precision. Errors in target ephemeris, beam direction, launch velocity, clock, and later attitude accumulate into a missed distance at arrival. A microscopic angular error near Earth becomes a vast lateral separation at Proxima. Imagine extending a line across 40 trillion kilometers. Moving its far end by the scale of a planetary system requires only a slight change in angle at the beginning. You need both an accurate launch and some ability to refine the path. The engine remains behind, but not every correction requires a conventional rocket. Tiny photon thrusters, controlled reflection, sail orientation, or other low-mass methods may provide limited steering. The exact system remains part of the unresolved design. What matters is that your correction budget is small. You cannot turn around. You cannot choose Alpha Centauri A halfway through because a new planet looks more interesting. You can trim an appointment. Navigation uses the sky. A star tracker compares observed patterns with a catalogue. Your motion creates relativistic aberration that shifts apparent directions, and Doppler effects alter observed frequencies depending on whether light approaches from ahead or behind. At 20% of light speed, these effects are significant enough to model, but they are calculable. The universe has not changed its rules. Your moving frame has changed the measurements. The tracker also needs to survive an altered instrument. Suppose radiation damages part of the detector. Software can ignore known bad pixels and compare multiple stars. Suppose attitude drifts. The sail or tiny control system can rotate you back. Suppose the clock has shifted. Pulsars or other stable astronomical references might support timing in a larger architecture. While a gram-scale design must balance such capability against mass and power, every elegant navigation idea must fit on the same wafer carrying the science. Can you correct your path after the engine remains behind? Only within the authority carried on board. The laser launch must do most of the work. Later systems can refine, not rescue, the trajectory. The answer is therefore conditional. Yes, for small errors anticipated by the design. No, for a fundamental launch direction or velocity failure. You survive the first navigation update. The target estimate changes by a tiny angle. Your attitude system responds. There is no cinematic turn. A small pressure or photon impulse accumulates. The correction is measured in numbers that would look insignificant on a dashboard. At Alpha Centauri, those numbers decide whether your camera passes close enough to see a planet as more than a bright point. Then you return to low power. Years pass in the narration, because most of your mission is waiting without becoming dead. Earth continues around the Sunday. The laser array is repaired, upgraded, perhaps used for other missions. People who built your first control software leave the project. New astronomers improve the orbit of Proxima b. New receivers become more sensitive. Your physical hardware remains the version that departed. Interstellar travel makes obsolescence one-directional. Earth can modernize the equipment, listening to you. You cannot modernize the equipment speaking. Commands can still overtake you because radio and laser signals move at light speed. Engineers may upload corrected target information, revised observing schedules, or software patches. The message takes longer each year, and any update must be safe for hardware whose current condition Earth does not know. A patch written from old telemetry can arrive after another component has failed. Your software must therefore treat Earth as a source of delayed suggestions, not immediate authority. It verifies commands, checks resources, and decides whether execution remains possible. If a message requests an instrument that no longer responds, you cannot explain the conflict in real time. You choose an alternative or preserve power. The relationship between probe and mission control has quietly reversed. During launch, Earth supplied almost all your energy and direction. During cruise, Earth supplies knowledge but cannot supply action. Near arrival, you will own every decision that matters. Another wake cycle begins. Your clock reports that the cruise is halfway complete. The number is meaningful only under the assumed speed and trajectory. There is no halfway marker outside. No sign floats in interstellar space. The sun behind and Proxima ahead remain points, and the space between them offers no road surface. Your body checks memory. Scientific data collected during cruise may include particle counts, fields, and impact records if your instruments and power allow. Those measurements are not merely background material before the destination. Humanity has sampled the local interstellar environment near the heliosphere, but a fast traverse toward Alpha Centauri would provide a new path through it. Every impact that does not destroy you can become information about the road. Sending that information continuously would reveal health and reduce the mystery of failure. But transmission costs power and demands pointing. Saving everything until arrival risks losing all cruise data with one late failure. A mission may compromise through occasional low-rate beacons, distributed probes, and stored high-value summaries. Silence is therefore ambiguous. It may mean planned sleep. A failed transmitter may have lost its pointing. The probe itself may be gone. Earth can design expected contact windows, but it cannot force a whisper from hardware with no energy. You wake again. This time, one memory block reports errors. Redundant encoding reconstructs the stored state. The damaged region is isolated. The event is not a factual prediction for a real craft. It is a labeled scenario showing what autonomy must do. You continue with less storage and a revised schedule. Congratulations. You survived being obsolete. The 5th and 6th opening questions have their answers. You can make limited corrections after leaving the engine, and sleeping hardware can, in principle, wake after decades if clocks, power, memory, and fault management endure. Neither capability is demonstrated for a complete relativistic nanocraft. Both are core mission requirements, not details to be solved after propulsion. Ahead, Proxima's light is becoming more important to your instruments. The long sleep is ending. For most of the cruise, Proxima Centauri was a navigation promise. Now its light begins changing fast enough to organize the mission clock. Your instruments wake more often. Power stored slowly over years is assigned to a sequence that cannot be repeated. Memory is cleared for encounter data. Attitude control prepares to point the camera at a target no human can currently see as a resolved world. You have traveled for more than 2 decades under the assumed starshot-like performance. Earth has watched only delayed telemetry, occasional beacons, and the continued absence of evidence that every probe failed. The people waiting at home cannot see what you see now. Your observations will need more than 4 additional years to reach them. The star ahead is a red dwarf, much smaller and cooler than the Sunday. Proxima is so faint that it cannot be seen with unaided human eyes from Earth despite being the nearest star. Its low luminosity draws the region receiving moderate stellar energy close to the star. Proxima b completes its orbit in roughly 11 days within that region, often called the habitable zone. The name sounds more generous than the evidence. A habitable zone identifies orbital distances, where a planet with suitable conditions could allow liquid water at the surface. It does not demonstrate that water exists, that an atmosphere survives, or that the surface resembles Earth. Proxima b is a roughly Earth-mass planet, and a compelling target precisely because those larger questions remain open. Its star is active. Proxima produces flares and bursts of high-energy radiation that can affect atmospheric chemistry and potentially contribute to atmospheric loss. Whether the planet has retained substantial air depends on history, composition, magnetic environment, replenishment, and other factors not settled by the phrase habitable zone. Your camera is not approaching a confirmed refuge. It is approaching the nearest world where ignorance can become local measurement. The target sequence loads. Your navigation system compares the predicted star field with the observed one. Proxima has shifted from the delayed position measured at launch, but the intercept model expected the motion. The planet itself remains difficult. It is small, close to a bright star from your perspective, and moving quickly around its orbit. You need timing, not merely direction. At 20% of light speed, you cross one astronomical unit in roughly 40 minutes. Proxima b orbits far closer to its star than Earth orbits the Sunday. The useful geometry for close images can pass in a short interval. 20 years of crews have purchased an encounter that may fit inside a working day. This is where speed reveals its second face. You have no large engine pointing backward. The laser array that accelerated you is 4 light-years away. Proxima has no matching facility waiting to catch the sail. Gravity can bend your path, and starlight can push on reflective material, but a high-speed flyby architecture does not automatically become an orbiter because it reached the correct coordinates. You are moving too fast to stay. Can you slow down when no laser waits at the destination? Not under the simplest fast sail architecture. A change in velocity requires a physical interaction. Expelled propellant, light pressure, magnetic forces, particle interaction, gravity combined with another force, or some other mechanism that actually changes momentum. The word arrival supplies no break. Researchers have examined slower photon sail routes that could use the light and gravity of Alpha Centauri A and B to decelerate and redirect an ultralight sail, perhaps eventually toward Proxima. Such photogravitational assist concepts trade cruise speed for capture capability. They require extraordinary sail properties, precise stellar encounters, favorable geometry, and travel times much longer than the fastest flyby. Magnetic charging and stellar fields can complicate the path. Other advanced concepts consider magnetic sails, fusion propulsion, particle beams, or antimatter-assisted deceleration. They identify physical possibilities and engineering requirements. They are not hardware available for this mission. The honest version of your design remains a flyby. That limitation is not discovered at arrival. It was chosen at launch. Your small mass and high speed made a 20-year crossing plausible. Carrying a powerful braking system would have increased mass, changed the sail, reduced acceleration, and possibly demanded a completely different architecture. The mission traded time in the system for time reaching it. You survive the realization that arrival is not a stop. The camera begins its sequence. It cannot point the way a person turns their head. Your entire body or an optical element must reorient. The navigation software identifies Proxima, estimates the planet's location, and schedules short exposures. Relative motion threatens blur. The star threatens glare. Available aperture limits detail. Power limits how many images and measurements can be made. You cannot ask Earth whether the first frame is centered. A message requesting advice would arrive after the flyby, and any answer would return years later. The encounter logic chooses exposure, pointing, compression, and priority using rules written before the people receiving the data know whether Proxima b has clouds. What appears depends on distance and instrument performance that no final mission design has yet established. We should not invent a blue ocean, continents, lights, or even a thick atmosphere. Imagine only what the scenario supports. A resolved or partially resolved planetary target producing photons that your detector records. The pattern may later constrain surface brightness. Clouds, atmosphere, thermal conditions, or geometry. What the pattern means remains for analysis on Earth. Your instruments may also sample magnetic fields, charged particles, dust. A close passage through another star's environment would provide measurements no telescope can obtain from Earth. Even a barren planet would not make the journey scientifically empty. The interstellar road and the stellar neighborhood are targets too. Proxima b passes closest. The useful interval ends almost as soon as the narration learns to inhabit it. You do not enter orbit. You do not turn around for a second look. The planet moves behind. Proxima shifts across the instruments, and your stored velocity carries you outward. Congratulations! You reached the Alpha Centauri system. You did not stop. Does a flyby lasting hours count as arrival? Under the objective established at the beginning, yes, if you cross the target region, gathered local data, and can return that data. Under a promise to orbit, land, or remain, no. Reach is not a scientific unit. The mission contract decides what the word means. This is why the opening gave you a narrow goal. You were trying to make one human-built machine reach Alpha Centauri while it could still speak. Crossing the system satisfies only the first half of that sentence. The memory now carries the result. The transmitter must deliver the second. Before transmission, you decide what to keep. A camera can produce more raw data than a gram-scale interstellar probe can easily send. Images may need calibration, selection, compression, and error protection. Repeated frames can improve confidence but consume storage and transmission time. Particle measurements compete with pictures. Housekeeping information competes with both because Earth needs to know whether an odd scientific value came from the environment or a damaged instrument. Your processor ranks the packets. A few key images receive strong error correction. Navigation and timing data accompany them. Cruise impact records survive in summaries. Some raw information is discarded because preserving every bit would prevent the most important bits from leaving. This may feel like destroying treasure. It is actually the final form of instrument design. Data that cannot be transmitted is not automatically useless, but it cannot fulfill a mission whose laboratory remains on Earth. The science package was always constrained by the communication link. You turn toward home. Earth cannot be seen as a separate bright dot beside the Sun from every geometry, but the Sun provides a strong reference. A star tracker and predicted ephemeris help aim the transmitter. The pointing tolerance depends on wavelength, aperture, beam divergence, and receiver design. A narrower beam preserves more intensity at Earth and makes missing easier. The sail may become part of the optical system if it remains attached, intact, and controllable. Proposed concepts examine using a compact laser on board, storing power, and transmitting in bursts. The original terrestrial array or another immense collector can listen. Detectors search for individual photons arriving in a recognizable coded pattern. Light does not weaken because it becomes tired. A beam spreads. The photons are distributed over an area that grows with distance. Your transmitter has little power and a small aperture. Earth compensates with collecting area, sensitive detectors, long integration, coding, and patience. Physics allows photons to cross the distance. The unresolved engineering question is whether your tiny power and optical system can direct enough detectable photons at a useful data rate after decades of damage and aging. Communication may be harder than acceleration. A swarm can help. If many probes survive and control timing well enough, their signals could combine or provide repeated independent data. Even without coherent combination, several transmitters increase the chance that Earth hears at least one. Different trajectories may offer different viewing angles and encounter distances. Your first transmission is not the image. It is a beacon. A short coded pattern identifies the probe, confirms the encounter time, reports remaining power, and tells Earth where to search for later packets. Energy accumulated over a long interval is released in a brief optical burst. Then you wait and recharge. The photons leave. They travel toward the Sun for more than 4 years. During that time, you continue moving away from Proxima. The people on Earth see only the old system and the expected arrival window. They cannot know that the first signal is already crossing the dark. The camera question remains open on their side. Your camera may have succeeded. Success is not shared until information arrives. You transmit again. The message is weaker than any dramatic radio voice from fiction. It is a pattern of arrivals inside a detector, separated from background and reconstructed through mathematics. Clouds, atmosphere, telescope optics, and pointing influence an Earth-based receiver. A space-based receiver avoids some atmospheric problems and creates others involving cost, aperture, alignment, and operation. The receiving institution must survive too. Files describing your encoding, clock, expected path, and calibration cannot be misplaced when software generations change. The original engineers may have retired. The detector may use technology that did not exist at launch. Future scientists need enough preserved context to understand an old machine's faint language. An interstellar mission therefore sends two spacecraft. One is you, the other is a chain of records, receivers, people, and institutions remaining on Earth. If either fails, the data does not complete the journey. 4 years pass for the photons. The first burst reaches the solar system. A receiver records a pattern matching the predicted code. Independent instruments examine it. The timing aligns with your trajectory. Error correction reconstructs the beacon. Congratulations. You survived communication. Not because a real Alpha Centauri probe has already demonstrated this link. You survive within a labeled mission scenario that assumes the beamer, sail, nanocraft, autonomy, and receiver have each crossed their development gates. The point is not to present the mission as scheduled, it is to reveal what success would require. The beacon pays the last opening question. A tiny transmitter can, in principle, send useful information if the complete optical link supplies enough power, pointing precision, collection area, coding, and time. The image arrives later, reconstructed slowly rather than appearing instantly on a screen. Earth finally sees what you saw. By then, the flyby is more than 4 years old. The first recovered image does not answer whether humanity has found another Earth. It answers a smaller question. What pattern of light entered your detector during a brief passage near Proxima b? Scientists calibrate the response, compare frames, correct for motion, and test whether apparent features belong to the planet, the instrument, compression, or noise. This is how an interstellar revelation may actually arrive, not as a perfect globe appearing on a screen, but as a reconstruction that survives every effort to explain it as an error. If the data show an atmosphere, the result opens questions about composition, pressure, clouds, circulation, and survival under Proxima's activity. If the data suggest little or no atmosphere, that result matters just as much. A habitable zone orbit never guaranteed habitability. The closest potentially temperate planet is valuable whether it becomes a refuge, a warning, or a world unlike any simple category. Your local particle and field measurements help interpret the image. Stellar flares are not merely bright events seen from Earth. They shape the space surrounding Proxima. A probe near the star can measure energetic particles, magnetic structure, and plasma conditions directly along one path. Those measurements can improve models of how the environment interacts with planetary atmospheres. The result may be frustratingly incomplete. A single flyby samples one geometry at one time. Weather can hide a surface. Illumination can place important regions in darkness. Your closest approach may miss the intended distance. A tiny camera cannot perform every observation imagined during 20 years of waiting. This does not make the mission a failure. It defines the next one. The second probe generation can carry instruments chosen from evidence rather than desire. If clouds dominate, it can observe wavelengths that probe different depths. If the magnetic environment is violent, it can improve particle sensors and shielding. If communication limited the first return, the receiver and transmitter can change. If navigation missed, the launch and correction architecture can tighten. Exploration turns a point of ignorance into a list of measured constraints. You continue transmitting as your distance from Proxima grows. Each packet takes slightly longer to reach Earth than the previous one because you are moving away from home and the system. Your remaining power declines. The beam must remain pointed toward a receiver that is now even farther behind. You cannot use the encounter to refill a battery or repair a coating. Starlight near Proxima briefly offered more energy, but a flyby passes too quickly for a tiny system to transform itself into a new spacecraft. The mission after encounter is a controlled exhaustion. Release the stored knowledge before the systems that carry it fall silent. This is the first meaning of while it can still remember how to speak. Memory without power is a sealed archive. A transmitter without pointing is a lamp shining away from every listener. A receiver without the code hears only background. Communication succeeds only while all three remain aligned. Earth reconstructs another packet. It contains the impact history from crews. The pattern helps estimate dust and gas along the route, although the sample is filtered by your shielding and survival. Probes that failed cannot report the impacts that ended them. Scientists compare data from multiple surviving craft to reduce that bias. Another packet contains starfield observations made during approach. Those measurements refine the local geometry of Proxima and its relation to the bright pair. Alpha Centauri A and B may have appeared as strong distant lights from your route, but you did not visit them. Your trajectory was written for Proxima. That limitation matters because Alpha Centauri is a system, not a single destination. Alpha Centauri A resembles the Sun more closely than Proxima does. Alpha Centauri B is somewhat smaller and cooler. The two orbit one another on an approximately 80-year cycle. In 2025, observations with the James Webb Space Telescope produced strong evidence for a possible gas giant around Alpha Centauri A. The object remains a candidate, not a confirmed second Earth, and its possible nature is closer to a Saturn mass world. Suppose later observations confirm it. Your mission still cannot turn toward A. The separation between Proxima and the bright pair is enormous on the scale of planetary systems. At your speed, a crossing might be possible in additional time, but you are already moving along a flyby trajectory, with limited control, declining power, and no reason to assume the geometry aligns. A named system does not make its members one compact target. This pays a question that the title hides. Which Alpha Centauri are we trying to reach? The nearest member is Proxima. The most Sun-like member is A. B offers another stellar environment. A mission must choose. Saying Alpha Centauri without an encounter plan is like saying the ocean without naming a shore. Future missions could aim for A and B, perhaps using one star's gravity and light in a braking strategy. They could search locally for smaller planets difficult to separate from stellar glare at Earth. They could measure the winds and magnetic environments of two sun-like stars. A slow sail designed for photogravitational assists might attempt to sequence through the system. Those missions would not simply be better versions of you. They would optimize a different promise. To remain near a star, the craft may need to arrive slower. To carry larger instruments, it may need more mass. To navigate among three stars, it needs greater control and lifetime. A design that wins the race to first data may lose the contest for depth. The word nearest has now broken into choices. From Earth, 4.25 and 4.35 light-years seem almost equal. From inside the mission, tenths of a light-year can represent another major journey. Proxima's orbit around the other two takes more than 500,000 years because the separation is so large. The system's name is a gravitational relationship, not a promise of convenient travel. You transmit the final high-priority image. The power system estimates that another full science burst may be possible after a long recharge. Housekeeping data receive lower priority. The transmitter cools. Your processor checks pointing and enters a reduced state. You survived the destination, not in the sense of being captured by it. You survived passage through its local environment long enough to convert the encounter into returning photons. The system is already behind, but the information continues toward Earth. Now, imagine the next mission refusing to accept a flyby. It wants orbit. That single word changes the ship before it leaves. A captured probe needs to lose nearly all the relative velocity that made your short crossing possible. It may carry propellant and an engine, use an ultralight sail against stellar radiation, deploy a magnetic structure, or rely on another physical interaction. Every method adds mass, area, timing, and failure modes. If a craft carries its own braking propellant, the launch system must accelerate the propellant too. More launch mass requires more beamed energy, a larger sail, a longer acceleration distance, or a lower speed. If the craft relies on stellar light, its sail must survive, cruise, deploy, or reorient near arrival, and follow a trajectory close enough to a star for useful pressure without being lost to heat or navigation error. Photogravitational studies demonstrate that light pressure and gravity can, under modeled conditions, decelerate and redirect extremely light sails near Alpha Centauri A and B. The maximum arrival speed that can be captured is lower than the 20% light speed flyby considered for you. Lower arrival speed means a longer journey from Earth. Some modeled routes extend toward many decades or more before the probe can remain bound. This is not a defect hidden in the concept. It is the same trade stated honestly. Fast arrival and stopped arrival are different optimization problems. A probe taking 75 or 100 years could outlive its builders and still fit within an institution's historical memory. That sounds easier than a human generation ship and remains an extreme machine lifetime challenge. Electronics, power, sail material, communication, and autonomy must persist far longer. The receiver may belong to the grandchildren of the launch team. Historical studies such as Project Longshot explored massive fusion-driven probes with travel times around a century. Such designs imagined reactors, fusion propulsion, larger science payloads, and destination operations. They were detailed concept studies, not flown technology. Their value lies in exposing what a heavier mission would require rather than proving the requirements have been met. Fusion propulsion promises much higher exhaust velocity than chemical rockets. If a practical space system can be built, the ship could carry energy and propellant, accelerate over time, and brake at the destination. It would also need reactors or pulsed systems, radiators, magnetic control, shielding, fuel handling, long-lived structure, and autonomous repair. Controlled fusion propulsion for an interstellar vehicle remains undemonstrated. Antimatter contains even greater energy per unit mass, in theory. Proposed architectures examine using it for propulsion or deceleration. Producing, storing, controlling, and converting useful quantities safely is far beyond an available mission system. The word antimatter names a physical energy source. It does not fill in the engineering between laboratory particles and a starship. Magnetic sails attempt to interact with charged particles or stellar winds over a large effective area. They may offer braking without carrying conventional propellant, depending on environment and achievable structures. The interstellar medium near the destination. Deployment scale, field strength, mass, and control all matter. Again, the idea is a research direction, not an invisible brake attached to your wafer. There is a temptation to place every advanced concept in one imaginary spacecraft. A laser sail for launch, fusion for cruise, magnetic braking, artificial intelligence, self-repair, and a powerful optical transmitter. Combining names does not combine readiness. Each interface can create new mass and failure. An honest mission chooses a coherent architecture and accepts what it cannot do. Your architecture accepted a brief encounter. The next might accept a century. Neither makes a human passenger plausible by itself. That larger question is approaching. But first, the solar system must learn how to build the path that produced you. Because at the moment, even your gram-scale success remains a future conditional. To make you real, Earth must first build smaller versions of your story. The first test does not aim at Alpha Centauri. It places a sail where engineers can observe it, applies a modest beam, and measures whether the material remains stable. The objective is not a speed record. It is evidence that beam shape, sail curvature, reflectivity, temperature, and control behave together as the model predicts. A material can look promising in one test and fail the mission. High reflectivity at the laser wavelength may come with poor thermal radiation. A film can remain strong when still and wrinkle during acceleration. A stable sail in vacuum may respond differently when attached to a real payload whose center of mass is imperfect. Manufacturing variation matters because thousands of probes cannot each be a hand-tuned masterpiece. The next test increases power or duration. Another tests attitude control. Another sends a wafer-scale spacecraft into orbit and asks it to compute, sense, store energy, and transmit. A swarm demonstration examines timing and coordination. Optical receivers attempt to recover weaker signals across larger distances. Each experiment isolates a reason your mission could fail. That is slower than announcing a launch date and faster than discovering every weakness 4 light-years away. The beamer itself grows through stages. A small array demonstrates phase control. Larger systems compensate for atmospheric turbulence. If the final architecture remains ground-based, a high, dry site may reduce some atmospheric problems. Adaptive optics measure changing distortion and command corrections. Power storage releases enormous energy during the short acceleration window. Cooling systems remove heat from the laser, and optical hardware. No existing facility combines the full scale required by the most ambitious concept. Building one would be a major engineering and institutional project. It must operate safely around aircraft, satellites, and orbital debris. It must coordinate with international authorities because a powerful directed beam does not respect the administrative boundaries beneath its path. Range safety becomes part of your propulsion. If an object crosses the beam, the system must respond. If the array loses phase control, it must shut down safely. If weather degrades the wavefront, the launch may wait. The sail's departure window depends not only on planets and stars, but on the terrestrial atmosphere and everything moving through the sky above the array. This reveals an odd truth about your body. You weigh grams because the machine launching you may occupy kilometers and involve a global network of power, tracking, regulation, and receivers. Most of the Starship remains on Earth. Once built, that infrastructure could launch many probes. The high fixed cost belongs to the beamer and receivers. Additional sales may be comparatively inexpensive if manufacturing becomes reliable. A campaign can aim some craft at Proxima, others at Alpha Centauri A and B, and precursor versions toward targets inside the solar system. Those precursor missions matter even if the interstellar goal changes. A smaller directed energy system might send lightweight probes rapidly toward Mars. The outer planets, comets, the heliopause, or distant regions used for other astronomical experiments. It can test your technologies while returning science within shorter feedback cycles. This is how the path avoids becoming 20 years of faith after one launch. Solar system missions expose sails to real beam conditions: dust, radiation, navigation, low power, and optical communication. Engineers see what returns. Materials improve. Software learns from failures. The route to Alpha Centauri begins by changing how quickly small instruments cross home. The program also measures the interstellar medium more carefully. Spacecraft near the heliosphere detect incoming dust and particles. Future fast probes can sample directions farther out. No survey can identify every microscopic object along your exact path, but better distributions improve shield design and risk estimates. Astronomy continues in parallel. Telescopes refine Proxima's planets, stellar flares, possible atmospheres, and the Alpha Centauri A candidate. The target chosen at launch should not be based on a fashionable image from decades earlier. If new evidence shows another world or geometry offers greater science, mission design can change before the beam commits the trajectory. The desire to wait for better information creates another problem. Technology may improve while a slow probe is already traveling. A later, faster craft could overtake an earlier one and reach the target first. This possibility encourages delay. Why launch today if tomorrow's engine might erase the head start? The answer depends on evidence, not optimism. A later breakthrough is not guaranteed. Flight experience can create the improvement people are waiting for. A precursor with valuable local science may be justified even if a future craft overtakes it. A mission designed only to be first can become obsolete. A mission designed to learn can remain useful. Development time and travel time belong on the same clock. A 20-year cruise does not produce data in 20 years if the beamer requires many decades to mature and the returning signal adds 4 more. A slower architecture ready sooner might return information earlier. The shortest cruise is not automatically the earliest science. You exist at the end of that development chain. Your sail contains every material lesson. Your software contains every swarm failure. Your shield reflects measured impact distributions. Your receiver uses detectors, improved after years of optical tests. The final launch is not one invention. It is the point where many demonstrated systems are allowed to depend on one another. That dependence makes testing difficult. A sail can pass alone. A laser element can pass alone. A wafer can pass alone. The mission fails if their interfaces do. Thermal deformation changes beam riding. Beam pointing changes final navigation. Navigation changes communication geometry. Shielding changes mass. Mass changes acceleration. The complete system must close. This is why no honest date can be extracted from distance alone. Physics can calculate a cruise time at an assumed velocity. It cannot calculate when materials, funding, regulation, power infrastructure, and integration will become ready. Statements about launching within a generation describe goals, not appointments guaranteed by the universe. Suppose the program reaches a full demonstration. A carrier places many folded or protected sails into a suitable orbit. Each nanocraft deploys. Tracking systems identify it. The beamer selects one, acquires the sail, and begins the acceleration sequence. The process repeats. Not every launch succeeds. The mission expects loss and records why wherever telemetry allows. One probe leaves the beam at the wrong angle. Another sail heats beyond tolerance. A third loses contact. These are hypothetical failure modes, not invented mission history. Their purpose is to show why the campaign needs numbers and why early telemetry matters. A silent failure should not be the only teacher. You are one of the survivors. That phrase changes how credit works. Your path belongs to the material scientists who kept the sail reflective, the optical engineers who held the beam, the astronomers who predicted the intercept, the software teams who designed autonomy, the detector teams who heard the returning photons, and the institutions that preserved knowledge across careers. Interstellar travel distributes one mission across people who may never meet. The first generation builds the beamer. Another launches. Another watches the encounter clock. Another receives the final packets. A project that depends on one founder's memory is not an interstellar project. Procedures, calibration, code, assumptions, and uncertainty must remain readable. Documentation becomes a second spacecraft. It stays on Earth, moving through changing software, languages, organizations, and storage systems. If encoding details disappear, your signal can arrive and remain meaningless. If calibration records vanish, a planetary feature can be confused with detector behavior. If target assumptions are forgotten, later analysts may interpret a miss as an instrument failure. The mission must archive not only conclusions but reasons. Why was a wavelength chosen? Which material property was uncertain? What clock drift was expected? Which bits are housekeeping? Which frames were compressed most heavily? Future scientists need the chain that turns photons into evidence. This institutional demand is easy to underestimate because it has no rocket flame. It may be one of the few interstellar requirements we can begin satisfying immediately. Humans already maintain scientific records across generations, though never perfectly. Your mission asks that practice to become flight critical. Public expectations also need continuity. If the launch is sold as a guaranteed portrait of another Earth, uncertainty becomes failure. A truthful promise is narrower. Send defined instruments through a defined corridor, attempt defined observations, and return defined classes of data under stated assumptions. Partial success can then remain legible. A probe that misses Proxima b but returns stellar wind measurements fails the planetary objective and succeeds in local plasma science. A sail that reaches cruise speed but cannot communicate proves propulsion and fails information return. A transmitter detected without decodable science proves the link and fails the message. Difficulty alone does not turn every outcome into victory. The chain allows us to name which link held. This matters because silence has many causes. If no packet returns, Earth may not know whether the beam failed, dust struck, power died, navigation missed, the camera survived but the transmitter did not, or the receiver searched the wrong place. Redundant probes, cruise beacons, and staged tests reduce the ambiguity. The first interstellar failure might contain less information than a failed planetary lander, because the wreckage and final telemetry remain unreachable. That makes local testing and population statistics more valuable. The program spends cheap failures near Earth before accepting expensive silence near another star. What happens if we try with the hardware already flown today? We do not launch you. Current rockets can place spacecraft on trajectories escaping the solar system. Voyager, Pioneer, and New Horizons demonstrate that human-made objects can leave the planetary region and continue outward. None is an operating Alpha Centauri mission. None is aimed for a useful encounter there, and their velocities imply travel times measured in tens of thousands of years. The fact that an object will eventually pass through interstellar space is not the same as a mission to a star. A mission needs destination, navigation, lifetime, instruments, power, and communication designed for the crossing. Drifting for geological stretches with no operating system does not satisfy your opening objective. What happens if directed energy research succeeds at its ambitious scale? Then, a version of you may become one of the first plausible ways to return local data from another stellar system within a human career. The statement remains conditional. It does not hide the beamer, sail, dust, power, autonomy, pointing, encounter, and communication problems behind the word may. You are the smallest coherent answer to the distance that current serious concepts can imagine. And that is why the human answer is so much larger. To see how much larger, keep your destination and begin adding what a person needs. Your gram-scale body becomes a pressure vessel. The pressure vessel needs air, water, food, temperature control, radiation protection, waste processing, medical equipment, spare parts, and room for people to move. Add engines capable of changing its velocity. Add propellant or some other source of momentum. Add a power system that must operate when sunlight has become only another star. Add shielding for every system that now has to remain alive rather than merely functional. The payload no longer grows by grams, it grows by tons, and every added ton changes the propulsion system that must accelerate it. A larger propulsion system may require more propellant, larger tanks, more structure, and more thermal control. Those additions require still more propulsion. This is the familiar compounding penalty carried by rockets, extended into a mission where the required change in speed is far beyond any crude journey attempted so far. The laser strategy does not scale simply by making the sail larger. The force from light is gentle. It becomes useful for you because you are almost impossibly light, and because a vast external array concentrates power onto your sail. A human habitat has millions or billions of times more mass. Holding the same acceleration would demand a corresponding increase in force, while the sail must survive higher total power and remain controllable over a much larger structure. Reduce the acceleration, and the beam must follow the sail for longer. During that time, the target recedes, the spot spreads, and the array must maintain phase and pointing. Increase the sail area, and its flexibility becomes a greater control problem. Increase the beam power, and heat becomes more severe. Human scale does not violate one convenient number. It pulls several coupled limits at once. Suppose instead that the human craft travels more slowly. At 1% of light speed, a crossing of roughly 4¼ light years takes roughly 4¼ centuries before allowing for acceleration and braking. At 0.1%, the cruise alone lasts roughly 4¼ millennia. These are simple distance divided by speed estimates. They are not mission plans, because they do not include how the craft reaches that speed, stops, or supports its occupants. At 10% of light speed, the cruise falls to a little over 40 years. That sounds almost compatible with one lifetime. But the energy and impact environment are already transformed. A crewed ship would need to accelerate a vast mass to that velocity and remove nearly all of that velocity at the other end. Any propulsion architecture must account for both changes unless the travelers accept an extremely fast flyby after spending decades in transit. Braking cannot be a footnote. You can cross the Proxima system in hours because your mission is built around a brief encounter. A human crew cannot arrive that way. A habitat moving at a significant fraction of light speed would flash through the system before people could explore anything, then continue into interstellar darkness. To live there, it must carry or arrange a second act of propulsion comparable to the first. Some proposed interstellar studies explore fusion propulsion, antimatter-assisted systems, beam-driven craft, magnetic sails, or combinations of methods. They are proposals and research directions, not engines waiting in a warehouse. Each moves the burden to a different place. Fuel production, reaction control, waste heat, gigantic fields, external infrastructure, or material performance. Naming a propulsion family is the beginning of the accounting, not the end. Even a hypothetical engine does not erase the occupants. People consume oxygen and produce carbon dioxide. They drink water, eat nutrients, release waste, shed microbes, generate heat, become sick, and damage equipment through ordinary use. Space stations recycle important resources, especially water and air, but they are not sealed worlds independent of Earth for centuries. They receive supplies, replacement components, and continuing support from a planet only hours away by emergency communication. An Alpha Centauri habitat cannot assume that relationship. After departure, no cargo vehicle catches it with a new pump. No ground team sends a physical valve. No hospital receives a patient. Even a radio consultation becomes increasingly delayed, and the answer remains advice rather than rescue. The ship must turn a narrow, manufactured environment into its complete biosphere. Closing the water loop is only one part. Water hides in humidity, waste, food, cleaning, plant tissue, and chemical processes. Filters clog, seals age. Trace contaminants accumulate. Microbes evolve and move through places designers did not expect. A system that recovers a high fraction of water can still lose enough over centuries to become unsustainable unless reserves, repairs, and alternative processes cover the difference. The air loop has its own chemistry. Oxygen must be supplied or regenerated. Carbon dioxide must be removed. Trace gases from plastics, electronics, cleaning compounds, fires, biology, and manufacturing must be monitored. Pressure must be maintained despite leakage. A small error repeated for decades becomes a large inventory loss. Food is harder because it is not merely calories. People require proteins, fats, carbohydrates, vitamins, minerals, fiber, and a safe microbial environment. Stored food degrades. A multi-generational mission therefore points toward agriculture or another regenerative production system. Plants need light, nutrients, controlled temperature, water, carbon dioxide, pollination or mechanical help, disease management, and space. Their lamps and equipment produce heat that the ship must reject. A farm in space is also a failure surface. One pathogen can move through a genetically narrow crop. A pump failure can damage roots before a replacement is made. A harvest can be lower than planned. The crew needs buffers, seed diversity, multiple species, diagnostic tools, and enough surplus capacity that one bad cycle does not become famine. The habitat must process waste back into useful matter, without allowing toxins or pathogens to concentrate. On Earth, oceans, soils, weather, and enormous ecological networks distribute and transform waste. Inside a ship, the boundary is metal. Every atom stays in the human environment unless it is deliberately stored, recycled, or released. And released material is gone. This is not an argument that closed ecosystems are impossible. It is an explanation of what must be demonstrated. Long-duration experiments can test smaller loops. Lunar or Martian habitats could force systems to operate with less resupply. A credible interstellar design would emerge from evidence that the ecology remains stable through failures, maintenance, and biological change. Not from a diagram in which arrows form a perfect circle. Now add repair. Your nanocraft avoids most mechanical complexity because it survives a short acceleration, sleeps, wakes, observes, and transmits. A human ship contains pumps, valves, fans, bearings, pressure seals, wires, computers, sensors, medical devices, farm equipment, sanitation systems, and structural joints. Some parts can be redundant. Over centuries, redundancy alone becomes an inventory too large to predict. Repair, therefore, grows into manufacturing. The crew must diagnose a failed component, recover feedstock, fabricate a substitute, inspect it, and install it. A printer that makes simple shapes is not enough. Electronics require specialized materials and processes. Sensors need calibration. Lubricants and polymers age. Optical surfaces degrade. Pressure components demand quality control because a hidden flaw can become a rupture. Manufacturing machines also break. So do the tools that repair them. A self-sustaining industrial chain needs layers. Raw materials or recyclable stock, furnaces or chemical processes, precision tools, metrology, software, and people trained to connect them. The ship begins to resemble a small civilization because a small civilization is what can preserve complex technology without a supply line. Power must support that civilization every hour. Far from the sun, solar panels receive too little energy to serve a large habitat without enormous collecting area. A long-lived design would likely need nuclear power or another source independent of local starlight during cruise. The exact system remains a design choice, but its requirements are not optional. Fuel, conversion hardware, shielding, control, heat rejection, maintenance, and safe behavior after faults. Waste heat has nowhere to go except radiation. On Earth, air and water carry heat away from equipment, and the planet ultimately radiates energy to space over a huge surface. A spacecraft uses radiators. More power means more heat, larger radiators, or higher operating temperatures. Radiators are broad structures exposed to the same interstellar impact environment the rest of the ship faces. The frontal shield also changes character. Your tiny probe can place a small sacrificial layer ahead of critical electronics. A habitat has a much larger cross-section and a much longer list of things that cannot be lost. At high speed, dust grains release their energy into the shield through violent heating, ionization, and fragmentation. Gas atoms contribute erosion and radiation effects over the entire voyage. Making the shield thicker adds mass. Giving it distance from the habitat adds structure. Using magnetic or electric fields may deflect charged particles but not neutral dust in the same way. Placing expendable material ahead of the craft could absorb impacts, but that material must also be accelerated. The faster the habitat moves, the more demanding the shield becomes, and the heavier shield makes that speed harder to reach. Radiation arrives from more than the direction of travel. Galactic cosmic rays pass through space from many directions. Solar energetic events disappear as a concern once the sun is distant, but the ship loses Earth's magnetosphere and atmosphere from the beginning. Massive shielding can reduce some exposures, yet secondary particles created inside shielding complicate the problem. Long duration turns a low rate into a lifetime dose. Human bodies also need gravity or a substitute for its effects. Crews in orbit experience changes in bone, muscle, vision, fluid distribution, cardiovascular function, and other systems during months of microgravity. Exercise and medical countermeasures help, but an interstellar habitat cannot assume that decades or generations in weightlessness are safe. Rotation can create artificial gravity. A habitat or pair of modules can spin so occupants feel an outward acceleration against the floor. The radius and rotation rate determine the experience. A small radius requires faster rotation and may produce uncomfortable differences between head and feet, or strong effects when a person moves. A larger radius demands more structure and careful control. No human has been born, developed, and aged in reduced or artificial gravity. We do not know whether reproduction and childhood would proceed safely under the conditions a ship could provide. That is not a dramatic secret. It is an absence of evidence created by the fact that human spaceflight has been short compared with a lifetime. Medicine becomes more difficult across generations. The founders can be selected and screened, but their descendants cannot be pre-selected. Injuries, infections, dental problems, pregnancies, cancers, genetic disorders, and mental illness remain possible. A hospital must function with limited staff, limited pharmaceuticals, and no specialist arriving from outside. Medicines expire or degrade. Producing them may require biological cultures, chemical synthesis, sterile facilities, and quality testing. Surgery requires equipment, anesthesia, blood management, and trained people. Training cannot reside in one physician because that person ages. Knowledge must be taught repeatedly without allowing rare but critical skills to vanish during quiet decades. Population size introduces another coupled problem. Too few people increase the risks of lost expertise, demographic accidents, and restricted genetic diversity. More people increase habitat mass, food production, power demand, waste processing, and social complexity. There is no honest universal minimum that can be inserted without specifying reproductive technology, stored genetic material, voyage duration, health assumptions, and acceptable risk. Frozen embryos or large genetic archives could change some of that accounting. They do not raise children. A functioning society must still manage pregnancies, births, caregiving, education, consent, and medical uncertainty. If artificial gestation ever becomes practical, it would change the architecture again, but it is not a mature interstellar life support system today. Suspended animation offers another apparent escape. If adults could sleep safely for decades, the ship might reduce food, activity, and psychological demands. Human hibernation for an interstellar voyage has not been demonstrated. Even a deeply reduced metabolism would not automatically stop radiation damage, tissue changes, equipment failures, or the need for active caretaking. A sleeping crew makes the autonomous ship more responsible, not less, so the voyage remains lived time. At 1% of light speed, no founder reaches the destination. Generations are born into a machine they did not choose to launch. They inherit an objective selected centuries earlier by people known only through records. The destination may remain scientifically fascinating, but the social meaning of the mission changes. A generation ship is not merely a long spacecraft. It is a government, an economy, a school system, a medical system, an ecology, and a culture operating inside a pressure hull. Rules must remain legitimate after the founders are gone. Skills must be distributed. Conflict must be resolved without exile to another country. Resources must be allocated when a failed harvest or power problem makes every decision personal. The mission cannot assume permanent enthusiasm. Some descendants may value arrival, others may see the objective as an inherited constraint. Preventing them from changing course would require power. Allowing them to change course means the original mission is not guaranteed. Engineering can define a trajectory. It cannot pre-write centuries of human consent. Language and interpretation drift. Technical records can become ceremonial rather than understood. Maintenance procedures may survive while the theory behind them fades. A healthy design would preserve education, experiment, and the ability to challenge old instructions. The culture must know not only what to do, but how to discover when an instruction is wrong. This echoes your documentation problem, enlarged from a receiver team to an entire society. Your archive must tell future scientists how to decode photons. Their archive must tell future citizens how to keep air breathable, power stable, and decisions accountable. Psychology cannot be reduced to entertainment storage. The travelers live in confinement with a small population, limited privacy, repetitive surroundings, and no possibility of returning to Earth. Windows reveal stars whose positions change almost imperceptibly. Communication with Earth slows from minutes to years of one-way delay. Messages can still matter. A ship could exchange science, art, history, and personal records with Earth. Near Alpha Centauri, a question sent home waits more than 4 years to arrive, and another 4 for the answer. The people who asked it change before the response returns. Earth itself changes. Over a 4-century trip, nations, institutions, software, and languages can transform. The ship may be remembered as a central human project or become peripheral. The travelers cannot base safety on continuous political attention from home. A receiving society may continue to listen, but the mission must survive even if no useful instruction ever comes back. Navigation for a slow, massive ship is less frantic than your final flyby but more consequential. The craft has time to observe stars and refine its path. It also must preserve engines or another control method for centuries. Small errors accumulate. Moving stars, planets, and possible debris fields must be tracked. Arrival maneuvers need reliable maps made with data that may improve long after launch. The target will not wait in the position painted on departure day. Alpha Centauri A and B orbit one another. Proxima lies far from them and follows its own long relation to the system. Planets move. A human mission must choose whether it is going to Proxima, one of the sun-like stars, a specific planet, or a stable staging region. Alpha Centauri is a system, not one address. The destination also refuses to promise a home. Proxima b is approximately Earth mass and orbits within the region where liquid water could be possible under suitable atmospheric conditions. That description does not establish oceans, breathable air, a safe surface, or life. Proxima is an active red dwarf. Observed flares and high-energy radiation make the planet's atmospheric history and surface environment major questions. The candidate reported around Alpha Centauri A in 2025 remains a candidate, and the observations described it as a gas giant possibility rather than a second Earth. Future telescopes may discover smaller worlds, revise or reject candidates, and constrain atmospheres. The information available when a human mission could launch would almost certainly be richer than today's, but richer does not mean favorable. A crew cannot arrive depending on an unknown planet to supply air, food, water, or protection. Its habitat must work independently through crews and continue working after braking. If local resources are usable, they become an advantage after robotic surveys verify them. Until then, the starship carries its environment across the gap. Terraforming cannot rescue an arrival schedule. Changing an entire planet, if physically and ethically possible in a particular case, would demand vast time, energy, and understanding. The first settlers would still need closed habitats. A world with native life would introduce a different question: whether humans have the right to transform it at all. Planetary protection becomes more than avoiding contamination in a sample tube. A human habitat carries an ecosystem of microbes. If another world hosts independent biology, careless contact could damage both the alien environment and our ability to understand it. Isolation, observation, and restraint would belong to the arrival design. If no suitable planet exists, Alpha Centauri can still be a destination for science or space habitats. The crew might use asteroids, moons, stellar energy, or manufactured structures if accessible resources are confirmed. But then the mission is not a simple passage from one Earth to another. It is the transport of civilization-building capability into an unfamiliar system. This is the true scale correction. When you add humans, the objective changes from moving a machine to moving a self-maintaining world. The distance did not suddenly become longer. The meaning of survival became deeper. For you, survival until encounter means the sail, wafer, power, clock, instruments, and transmitter perform enough of their jobs. You need no food. Agreement is irrelevant to you. No descendants must keep believing in Proxima for your sake. A human craft must keep physics, biology, technology, and society inside acceptable boundaries at the same time. That is why a robotic precursor is not a lesser version of the human dream. It is the instrument that prevents the dream from using ignorance as a foundation. Your images can test whether Proxima b has an atmosphere visible in the data. Your measurements can sample the stellar wind and dust. Probes aimed at other members of the system can search for planets and characterize local conditions. One flyby cannot answer everything. Your instruments are tiny. Your viewing time is brief, and your signal is narrow. Yet local measurements would break uncertainties that telescopes cannot fully remove. Later craft could carry different instruments or arrive along different geometries. A swarm can turn one instant into a sequence. If breaking concepts mature, a later robotic mission could remain in the system and watch weather, orbits, flares, and atmospheres over time. That would be a different architecture with a longer flight or more complex sail trajectory. The point is not that the first probe must do every job. It is that each mission should make the next decision less blind. Humans, if they ever follow, would travel behind layers of machines. Telescopes identify targets. Fast flybys test the medium and return close images. Slower probes examine the system for longer. Robotic industry might demonstrate local resource use before a crew depends on it. Communication relays could improve links. Navigation beacons could mark routes, although each beacon must itself survive and be worth the mass and mission needed to place it. There is no law requiring this sequence to end with people. The science may remain the goal. Society may decide the cost and risk of a crewed mission are not justified. New discoveries may redirect attention. A truthful interstellar program does not treat human settlement as an inevitable final frame. It treats knowledge as the next frame. Return now to the frame in which you are still the gram-scale probe. The larger human answer has clarified your purpose. You are not a miniature colony ship, and not a symbolic object thrown toward a famous name. You are a measurement designed to survive a chain of transitions. Each transition changes what can kill the mission, and no success at one stage cancels the next. On launch day, you do not begin beside the laser. You begin folded, protected, and almost lost among the systems that carry you away from Earth. An ordinary launch vehicle performs the first part of the journey because the beam cannot lift you through the lower atmosphere like a science fiction ray. The carrier places your group where sails can deploy, be tracked, and receive the planned light without crossing an unsafe corridor. This first ride is technologically familiar compared with everything after it, yet it can still destroy you. Vibration can crack an attachment. Contamination can change the sail's optical behavior. Deployment can wrinkle the membrane. A release mechanism can hold one corner too long. The interstellar mission can end before interstellar propulsion begins. That is why the sail reports what it can while Earth remains near. Cameras or optical tracking inspect its shape. The craft establishes its identity and orientation. The beam array does not assume that a folded object became a perfect mirror merely because a timer expired. Your first opening question was whether the sail can survive the beam that accelerates it. The honest payoff is conditional. Candidate materials and laboratory structures can be tested for reflectivity, absorption, temperature, strength, and stability. Smaller beam demonstrations can expose failure modes, but the complete sail must reflect enough light, radiate absorbed heat, hold its shape, and remain centered while the full propulsion system operates. Until that integrated event is demonstrated, survival is an engineering objective, not a fact. The array begins below full power. Its elements coordinate their phases, so their waves reinforce at your location. Tracking confirms that the sail responds. Control systems adjust the beam. Power rises. Light has no hand, but it pushes. Momentum carried by photons transfers to the sail as those photons reflect. For ordinary objects, the force is too small to notice. For your body, under a beam of extraordinary intensity, the force becomes a launch system with no propellant tank attached to you. The advantage is also the danger. A chemical rocket carries its energy and expels mass over time. Your energy source remains far away and concentrates on a surface thinner than any familiar spacecraft shield. If the sail absorbs a fraction that sounds negligible, that fraction can still become destructive heat. If the center of pressure moves away from the center of mass, the beam can amplify the error. You accelerate for minutes rather than years in the most ambitious fast flyby concept. The exact duration and acceleration depend on the final design. A gram-scale craft reaching a substantial fraction of light speed over such a short interval experiences acceleration far beyond human tolerance. Its solid-state components do not feel fear or lose consciousness, but their bonds, mounts, connections, and sail interface still carry load. The second question now returns. Electronics are not protected merely because they are electronic. Individual components can be selected and tested under high acceleration. The integrated wafer must prove that power, computation, sensors, connections, and structure remain functional through the launch pulse. There is no crew to tighten a loose contact afterward. The light behind you narrows into distance. Soon, the beam can no longer keep its energy concentrated efficiently enough to continue the same push. The engine remains on Earth, exactly as the opening warned. You leave it with whatever velocity and direction the acceleration phase produced. You survived acceleration. That sentence was the first payoff, not the ending. It opened the real antagonist because speed now belongs to you. The array can shut down, but your motion does not. Every kilometer ahead arrives quickly. Every correction is expensive. Every particle carries a larger consequence in your frame. During the first hours and days, Earth has its best chance to estimate the departure trajectory. Tracking stations observe the sail or signals from the craft. Small differences between intended and measured velocity are converted into a predicted miss years later. The sooner an error is understood, the more options remain. But the options are modest. You no longer have the launch beam following you through the whole crossing. A miniature craft might alter attitude, use tiny thrusters if included, change the way light acts on a sail, or exploit carefully designed onboard control. Each method consumes mass, power, material, or geometry. No gram-scale system carries an unlimited correction budget. This pays the fifth opening question before it pays the fourth. Yes, A path toward a moving star system can be calculated because astronomers measure stellar motion and orbital behavior. No, calculation does not freeze the target. Observations improve the predicted encounter. Onboard navigation compares reality with the plan, and corrections must fit within the craft's tiny capability. The sixth answer follows. You may correct your path after the engine remains on Earth, but only if the design includes a demonstrated control mechanism and only within its authority. A major launch error is not transformed into a minor software update. Accuracy at departure and correction during flight share the job. The sun shrinks behind you. The bright family of planets collapses into geometry. You pass beyond the region where conventional solar power is abundant. Your systems reduce activity. Sleep does not mean every circuit becomes dead. A clock or event system must preserve the sequence. Some sensor may monitor health or orientation. A receiver may listen during planned windows. Thermal conditions continue changing. Radiation continues striking. Materials continue aging. Keeping everything awake would spend power and expose more active electronics. Turning everything off creates a resurrection problem. The design needs a state between them. Enough function to preserve mission time and detect faults. Little enough consumption to endure the cruise. There may be scheduled awakenings. You check the star field, estimate orientation, inspect power, and perhaps send a sparse status signal. Frequent checkouts return more information, but consume more energy. Rare checkouts conserve energy, but allow a fault to remain hidden. The schedule is a risk decision written before anyone knows which fault will occur. Earth's ability to hear cruise reports decreases with range. A weak transmitter and tiny aperture spread energy over an expanding area. Eventually, the mission may choose silence because the power needed for a useful report is more valuable at encounter. Silence then stops being a simple diagnosis. It could indicate planned sleep. A pointing failure could produce the same result. The probe might also be gone. Engineers use redundant craft, known schedules, and whatever telemetry arrives to separate those possibilities. But some uncertainty remains all the way to the target. This pays the seventh opening question only at the end of the cruise. Can sleeping hardware wake after 2 decades? Components and architectures can be designed for long dormancy, radiation tolerance, low leakage, and fault recovery. Ground tests and precursor flights can build evidence. Yet the first full interstellar wake-up will be demonstrated only when a craft actually performs it after the real crossing. The answer is not guaranteed, yes. It is a requirement around which the mission is built. Between wake-ups, interstellar space acts on you grain by grain and atom by atom. The medium is thin, not empty. Gas particles strike the forward surface. Dust is much rarer and more massive. At your velocity, impact energy rises with the square of speed in the non-relativistic approximation, and more exact relativistic treatment becomes increasingly relevant as the fraction of light speed grows. Doubling speed does more than half travel time. It greatly increases the energy that must be managed in each collision. The third opening question asked whether a grain of dust can erase the mission in less than a second. For a sufficiently large grain striking a vulnerable place at a substantial fraction of light speed? Yes. No dramatic crater needs to be observed for that answer to be physically serious. Studies of relativistic spacecraft interactions describe heating, erosion, melting, and damage from gas and dust. The uncertain distribution of particles along one narrow path prevents an exact survival percentage from being stated honestly. The engineering response is layered rather than magical. Put sacrificial material forward, minimize frontal area, protect critical circuits behind other mass. Choose trajectories using the best available knowledge of the medium. Send many probes so one collision does not erase the entire scientific return. Examine damage on fast precursor missions. The swarm changes the meaning of one grain. It does not make the impact harmless to you. It makes the program capable of surviving your loss. That distinction is essential. Redundancy is sometimes narrated as if all craft arrived together in triumph. In a real risk strategy, some units may fail without announcing why. The mission succeeds statistically only if enough independent paths remain to perform the encounter, and enough signals can be separated at Earth. Independence is difficult because all probes may share one design flaw. A larger swarm does not solve a sail material that always overheats or software that always enters the wrong state. Diversity in launch conditions, hardware revisions, and software logic can reduce common mode failure, though diversity also complicates manufacturing and analysis. As years pass, astronomy on Earth continues. Better measurements refine Proxima's motion and planetary orbit. New planets may be found. Stellar activity is recorded. If you can receive updates, the mission may alter encounter priorities. A craft too simple to accept new information must rely entirely on what was known at launch. An update sent from Earth chases you at light speed. Because you move away at a fraction of light speed, the message still catches you, but later than a message sent to a stationary destination. Commands near arrival must be transmitted years in advance from Earth's calendar and interpreted by software that has survived the crossing. Earth cannot steer the final minutes by hand when your camera sees the target in large. The people who launched you are watching an old estimate of where you are. Your own sensors must identify the stars, distinguish targets, update timing, rotate the craft, control exposure, store data, and decide what to transmit. Autonomy is not artificial omniscience. It is a bounded collection of decisions tested against situations engineers can anticipate. The software may compare brightness patterns, reject saturated frames, prioritize scientifically valuable observations, and recover from defined faults. It cannot ask Earth what an entirely unexpected object means and receive an answer before passing it. Now the red point of Proxima begins to change. For most of the voyage, it remained star-like. Distance offered no sensation of approach. Near the end, geometry accelerates perceptually. Angles between destinations grow. The planet's predicted location becomes an actual search region. Your instruments wake fully, and the power saved across decades is spent in a sequence measured in days, hours, and minutes. The mission has a choice before the encounter. Aim closest to the star, the planet, or another region that provides the best combination of science and survivability. A close pass improves spatial detail but increases pointing rates and may expose the craft to a harsher stellar environment. A wider pass gives more time and a broader view but less resolution for the same camera. Proxima can flare. The encounter cannot count on the star behaving like a steady lamp. A flare may be scientifically valuable and hazardous at the same time, changing radiation conditions and detector exposure. Autonomous settings need enough range to keep a bright event from ruining every observation. Your camera does not take one final portrait and stop. It begins farther out with navigation images. It measures changing brightness and position. As distance closes, it records the star, the planet if geometry permits, dust, plasma, and any selected targets within instrument capability. Different probes can schedule different exposures, so one mistaken setting does not blind the whole swarm. If Proxima b is on the far side of its orbit, no software can move it into a convenient close approach. Launch timing and trajectory attempt to predict the geometry decades in advance, but orbital uncertainty propagates. A fleet spread across trajectories increases coverage at the cost of dividing resources. At a substantial fraction of light speed, the useful close encounter interval is brutally short. You cross distances comparable to a planetary system on the scale of hours. A human analyst cannot inspect one image and request another angle. The observation script unfolds before the first close data can reach Earth. This is where the 8th opening question receives its exact answer. Can you slow down when no laser is waiting at the destination? Not in the baseline fast laser sail flyby, merely because arrival has begun. You carry the speed the Earth beam gave you. Proposed photon sail braking trajectories would use light and gravity from stars in the Alpha Centauri system. But they require different speeds. Sail properties, navigation, and travel times from the fastest direct flyby. Other braking concepts add their own unproven systems. Deceleration is a separate mission architecture. And does that hours-long flyby qualify as arrival? For orbital settlement, no. For local scientific observation, yes. If the instruments obtain measurements that cannot be made from Earth and if those measurements return, the word arrival must name the objective. Crossing an invisible boundary is not enough. The encounter becomes a mission only through data. You pass the selected target. There is no sound. There is no sensation of wind. In front of you, photons shift and concentrate according to your motion. Behind you, the geometry changes too quickly for leisurely observation. Your control system turns the communication aperture toward a point near the Sun while science instruments complete their final sequence. Then Proxima recedes. Unless a braking system has altered the architecture, you are already leaving the system you spent decades reaching. You cannot turn around. You cannot wait for weather to clear. You cannot repeat a blurred frame. The camera's stored bits are now the most valuable mass you carry. The 9th opening question asks whether a transmitter smaller than a hand can send an image across more than 4 light-years. Again, the answer is conditional rather than mystical. The craft can aim a narrow optical signal toward the solar system, encode data with error correction, and transmit repeatedly. Earth can build very large receiving apertures or coordinated arrays, use sensitive detectors, and integrate faint arrivals over time. The link depends on available power, aperture, pointing, wavelength, background light, receiver scale, and the amount of data demanded. A tiny transmitter will not stream video as if Proxima were a nearby satellite. The mission may return bits slowly. It may send the most important measurements first, repeat them, then attempt images in prioritized segments. Compression saves bits but can discard detail. Strong error correction adds bits but protects meaning. Every choice spends a limited energy and time budget. Pointing is merciless. A narrow beam preserves intensity over distance, yet a smaller angular error can miss the receiver region. The craft must know its orientation and the future apparent location of the solar system. Earth moves around the Sun while the signal travels. The transmitter aims not at where Earth appears in an old observation, but where the receiving geometry will be when the photons arrive. Earth cannot tell you that the aim was wrong until years later, long after your useful power may be gone. The solution is to characterize pointing before launch, use guide stars, spread or scan the beam enough to cover uncertainty, and provide multiple probes or transmission attempts. Widening the beam increases coverage while reducing the photons per receiving area. The trade cannot be escaped. If the final link works, the message spends more than 4 years crossing home. Detectors must separate its photons from noise, archives must preserve calibration, and repeated packets must survive decoding. Only then do camera bits become evidence instead of an unreachable memory inside you. Now all 9 opening loops are closed, but one larger loop remains. What actually happens if we try to reach Alpha Centauri? The answer depends on what we allow the word "try" to conceal. If it means launching an existing spacecraft with today's flown propulsion and pointing it generally outward, the result is not a useful Alpha Centauri mission. The travel time is measured in tens of thousands of years, operating systems do not have demonstrated lifetimes on that scale, and the trajectory is not transformed into a planned stellar encounter by hope. If it means committing to an ambitious gram-scale laser sail program, the first decades may produce no interstellar image at all. They produce materials tests, beam control experiments, small sail flights, detectors, receivers, power infrastructure, navigation software, and failures close enough to study. The attempt begins as a research program before it becomes a departure. If those systems mature together, a swarm could be launched toward one or more targets in the Alpha Centauri system. The cruise could be on the order of 2 decades for concepts aiming near 20% of light speed. The return signal then adds a little more than 4 years after encounter. Those numbers describe the fast concept, not a guaranteed schedule or a completed vehicle. Some probes may fail during deployment, some may be lost during acceleration. Some may drift outside useful encounter geometry. Dust may remove others. Dormant systems may not wake. Cameras may work while transmitters fail. Receivers may hear only part of a message. The architecture accepts that possibility, without pretending failure is certainty. If enough craft survive, aim, observe, and communicate, humans receive the first measurements made inside the nearest stellar system. That is the most defensible near-term meaning of success. Not a person stepping onto a twin Earth, but information crossing the gap in both directions, machinery outward and photons home. If try means sending people, the answer moves much farther away. No present system can accelerate, protect, sustain, decelerate, and govern a human habitat through such a voyage. Faster travel intensifies propulsion and shielding. Slower travel transfers difficulty into centuries of ecology, maintenance, medicine, reproduction, and social continuity. The destination remains uncertain, even if the crossing succeeds. These are not separate pessimistic objections collected around one bold idea. They are the structure of the idea. Distance is the first number, but speed converts it into every other problem. Choose low speed, and the clock becomes the antagonist. Hardware ages. Biology must continue. Institutions must survive. Choose high speed and energy. Acceleration, heat, impact, navigation, and braking grow severe. The mission does not eliminate the distance. It selects the form in which distance will be paid. That is the delayed answer hidden inside your first burst of acceleration. It is speed. Speed lets a machine reach another star before its builders vanish into deep history. Speed also turns dust into a weapon, a small error into a distant miss, a planetary system into an encounter lasting hours, and arrival into a breaking problem as large as departure. The tool that solves time creates the rest of the plot. The probe survives by being small enough to accept that bargain. Humans cannot simply inherit the same design at a larger scale because mass changes the bargain. Their likely path, if one ever develops, will require different propulsion, vastly deeper life support, or a willingness to make the voyage a society rather than a trip. You remain the first kind of traveler because you need almost nothing. No cabin follows you. No oxygen circulates. No meal waits. No voice asks how many years remain. You carry a sail, sensors, logic, stored energy, and a message format. The civilization that built you remains mostly at home, embodied in the beam and receivers. This asymmetry is what makes the mission imaginable. Earth supplies the enormous launch power. You carry only what must cross the gap. Earth supplies the enormous collecting area. You return only a narrow signal. Infrastructure at home compensates for the body that had to remain light. Your success, therefore, cannot belong to the probe alone. If the beamer launches you but receivers are not preserved, the mission is incomplete. If the signal arrives but documentation is gone, it is incomplete. If one generation builds and the next refuses to listen, it is incomplete. Alpha Centauri requires coordination across distance and time on both sides of the journey. The attempt may still be worth making before every human question has an answer. A robotic mission does not require a generation ship to be ready. It can advance astronomy, propulsion, communication, autonomy, and our understanding of interstellar space. Its value should be judged against its actual scientific objectives and costs, not against a promise of immediate settlement. There is another result even before launch. Building a serious interstellar probe forces vague language to become measurable. Soon becomes a cruise velocity and development schedule. Reach becomes a flyby, orbit, or returned data set. Survive becomes a list of environments and durations. Image becomes aperture, distance, exposure, storage, and link budget. The dream becomes harder when measured, but it also becomes real enough to test. Tonight, from your room, Alpha Centauri can appear almost offensively ordinary. From much of Earth, it is one of the brightest points in the night sky, yet no visible gap reveals the trillions of kilometers between here and there. Its light crosses that distance without carrying the feeling of time. The photons entering an eye or telescope left the system more than 4 years ago. They complete the return half of your imagined mission for free, because stars already emit light. The hard part is sending an instrument into the scene so the returning photons contain a nearby measurement rather than a distant view. That instrument begins with a material thin enough to ride light. It becomes you. You wait above Earth while an array finds your sail. Somewhere below, the power systems are charged. Telescopes hold the target geometry. Receivers record your last near-Earth status. Other sails wait their turn because the mission has learned not to trust one path. The beam rises. For a few minutes, a machine built across the ground acts like the engine of something that will never carry its engine with it. Your speed climbs. Earth becomes the point behind you. The sail survives or it does not. The wafer holds or it does not. There is no narrator inside the hardware to soften the result. Then the beam ends. Ahead is no tunnel, no road, and no line drawn through space. There is only a predicted intercept with a moving system, a thin medium that can damage you, and a clock that must wake at the right moment. You coast through years that cannot be edited out of the physical mission. Earth changes while you sleep. Behind you, children grow into the scientists who may receive your data. The people who calibrated your camera preserve notes for colleagues they will never meet. Telescopes learn more about the planet you are approaching. Engineers launch successors that may carry better shielding, better clocks, or better transmitters. Ahead, Proxima continues to flare. Its planet circles without knowing it has been selected as a destination. Alpha Centauri A and B continue their orbit. The system is not waiting for humanity, and reaching it grants no control over what it contains. Years later, the wake command comes from your own clock. Stars return to the sensor. Orientation is estimated. Power flows into instruments that have not been fully active since the solar system was still close. The target brightens. Corrections, if any remain, become final. You do not stop. You do not need to stop for the mission you were designed to perform. That limitation was accepted before launch, written into every exposure and every bit of storage. Arrival is a measured passage rather than possession. The camera opens. For a short interval, humanity has an instrument inside another stellar system. It sees from a location no telescope near Earth occupies. It records what geometry and survival allow. Then its target moves behind. The transmitter turns home. Its first photon leaves with no assurance that anyone has detected it. The photon carries almost no energy, but it travels without fatigue. More follow in a pattern. Together they encode timing, health, and perhaps the first fragment of an image. 4 years pass around them. At Earth, a detector records something expected in a narrow region of time, direction, and wavelength. The event is checked. The pattern repeats. Noise begins to separate from intention. A packet closes. Error correction holds. Only then has the mission reached Alpha Centauri in the complete sense promised at the opening. Not when the carrier left Earth. Not when the laser pushed the sail. Not even when you crossed the target system. It happens when evidence returns and can be understood. The first successful arrival is therefore split across more than 8 light-years of cause and response. Machinery travels outward for over 4 light-years, and information travels back over the same gulf. The probe crosses space. The project crosses generations. The data closes the loop. If nothing returns, the attempt still teaches through every demonstrated stage before silence. But the central scientific promise remains unpaid. If a signal returns without an image, it proves some links and leaves others open. If local measurements arrive, even sparse ones, the nearest stars become places sampled by human instruments rather than points inferred only from afar. That change may look small beside the scale of the sky. It is not small. For all of human history, the stars have delivered light, while matter made by humans remained near one star. An operating probe at Alpha Centauri would break that boundary. It would not make interstellar space easy. It would make one crossing empirical, and the result would be quieter than the departure. No explosion marks the data's arrival. No object lands in a public square. A detector registers faint light. Computers compare patterns. Scientists argue over calibration. An image assembles slowly enough that its first pixels may raise more questions than they answer. That quiet is appropriate. The mission began by asking whether a gram-scale machine could remember how to speak. Its greatest act is not racing past a star. It is preserving meaning across the race. You are that chain compressed into a moving speck. Outside your imagined sail, the room has not moved. Air still presses against your skin. Gravity still holds every object without a rotating habitat. Water arrives through a civilization spread across a planet. Food, medicine, repair, and company exist because billions of people and a living biosphere support them. These ordinary conditions are the equipment a human starship would have to recreate. Look once more at the point of light. Its apparent stillness conceals 3 stars in motion. Possible worlds, violent stellar weather, and a distance that turns every design choice into a trade with time. The point is close by astronomical standards and almost unreachable by everyday ones. Both descriptions are true. You do not defeat that contradiction tonight. You give it a vehicle small enough to enter. A sail waits for light. A wafer waits behind it. A receiver waits years ahead of the signal it hopes to hear. Between them lies every unanswered engineering test, every grain the shield may meet, and every generation required to preserve the objective. Then, the beam touches the sail. For the briefest stage of the entire mission, acceleration is everything. Afterward, speed is everything. And at the end, one faint returning photon alone is enough to begin proving that the journey happened.